Hi, welcome back. In this lecture, I would like to give you a practical example on how to solve numerically a two-dimensional integral and how to perform a convergence test. The problem I want to solve is the following. I want to calculate the electrostatic potential phi on the symmetry axis along the z direction of a uniformly charged square. This plot here represents the problem I want to solve. So I have a square that is a uniform charge with the charge rho as naught, and the size of the square is a by a. The problem I want to solve is to calculate phi along this direction z along this axis. So for instance, given the size of the square and given the charge on this square, I want to be able to calculate what is the potential, for instance, at this point here along this axis. How we can calculate the potential? Well, we know from basic electromagnetics courses that the potential, for instance, in the position 0, 0 along the z direction can be calculated by computing this integral here, right? So the potential is expressed as rho over pi over the electric constant multiplied by this integral. So the goal of this lecture is to calculate this integral here, that is this part here, and perform a convergence test. So increasing the number of points and increasing the resolution, I want to see how the error is going down. So what is the strategy to calculate numerically this two-dimensional integral? To calculate the integral, a function of a and z over dx and dy numerically, requires the following steps. First, we split the square into n square, smallest square, of side h, equal to a over n. So this is our initial square, and then we divide it in squares, n square in this direction, and then n square in the other direction. The second step we want to apply is that on each small square we apply a simple integration rule. In this particular case, we are going to apply the so-called midpoint rule. After we calculate the integral for each of these squares, we basically sum it up. We sum it up all the contribution from the small square. So let's do the first step in our numerical integration. We want to calculate what is the integral on the small square, and our grid is constituted by many squares, right? N by n square. So let's first consider a single square of size dx times dy. So this is the following integral, and we can approximate by calculating by taking the center value of a function f at the center of the cell. Using a finite difference trick, we will focus on this technique in the next module of this course. We can apply a two-dimensional Taylor expansion to calculate this point here. We calculated the Taylor expansion point, the Taylor expansion at expansion point dx over 2 dy over 2, which gave the following expression here at the bottom. So this value here is actually equal to the value of the function at the center point multiplied by x coordinate multiplied by the derivative in x of f still calculated at the center point, plus a contribution from the y derivative that is y multiplied by the derivative of the function f in the direction y, calculating at the center cell point. Of course, the Taylor expansion includes several more terms. We decide to truncate our Taylor expansion and keep only these three terms, right? So a constant term, and then a term that depends on x, and a term that depends on y. And the truncation error will be of a big O of x squared plus y squared. So let's do this simple step. So we have our original integral, that is the integral for the small square. We do the simple trick of substituting this value here with the truncated Taylor expansion. So we just replace the expression we calculated from the previous slides, truncating the Taylor expansion. We just replace, and we will have basically four terms
For terms, we have the values that is constants, and then two values that are basically multiplying x by the derivative of f in x, a term multiplying y by the derivative in y, and plus the truncation error. So we can split it up, this integral, in at least in three parts. We keep the first part here. We can calculate this integral here, that is going to be 0. So we can, this term here, so this is constant value, so we go outside the integral, and then it will be the integral of x in the x, that is x squared over 2. And then, because we are calculating this integral between minus delta x over 2 and plus delta x over 2, these two terms will cancel out. The same will apply for this term here, that will cancel out. And finally, we have the term that is given by the truncation error. So what it remains from this fraction is this integral here, that is basically a constant, an integral of this constant value here that we can calculate easily. So this is going to be the values of f calculated at the center of the cell, multiplied by delta x and delta y, that is the size of the cell in the two directions. We have this term cancelling out because of the nature of the integral, and then we can calculate the integral for the truncation error. So this is equivalent to this term here, so we keep this term, and then we have the truncation error, that is this expression here. So in the case of a square, so the delta x is equal to delta y, so this integral will be simply the values of the function calculated at the center cell multiplied by delta x plus a delta x to the fourth. That will be our truncation error. So keep in mind that this is just the integral for one small square. Our domain consists of many of these squares. So what is the error over the whole square? Well, the error is going to be the error for one cell multiplied by the total number of cells. So this is going to be nx multiplied by ny multiplied by delta x, or because nx is equal to ny, this will be nx squared multiplied delta x 4. Our size, the size A can be considered size 1. So nx is also n1 is also 1 over delta x. So ny also is 1 over delta y, that is equal to delta x. So the whole expression will be 1 over delta x multiplied by big O delta x to the power of 4. So by dividing delta x to the power of 4 to delta x to the power of 2, we get a total truncation error that is delta x squared. So the truncation error has order 2, and the method is said to be second order accurate. So we developed a code to calculate the integral that I've explained in the previous slides. The code is in MATLAB. Let's go through quickly this MATLAB code. So the first thing we do, we calculate what are the coordinates of the edges of the nodes of the cell. So we have uniform equally spaced nodes in the x direction, in the y direction. We go from 0 to a, and then we use n plus 1 point, and then we have y that is going from 0 to a and is going to n plus points. We can calculate the grid spacing as a divided by n, and then we can calculate the square of the z direction. Remember that we get as an input at which height we want to calculate the potential, this is z, and we calculate z squared that we are going to use in the calculation of our integral. We are using the so-called midpoint rule for calculating this integral. I calculate this auxiliary point, and that is the square value of the x coordinate at the center of the cell, And so we calculate that for x square and y square. With this step here, I calculate what is the value at the center point by basically displacing of half center size, and then I square to I take the square, because we are going to use the square value of x s and the square value of x coordinate at the center cell and the square value of y at the center cell. We initialize at accumulator equal to 0, and then we go through all each square. So we are having n square along the x direction, n square along the y direction. So we have nested loops from I to 1 to n and j 1 to n that allows to go through all the square in our domain. So for each square we calculate the individual integral and we sum it up to the current accumulator value. So this is the integral that we calculate according to our formula using the midpoint rule. If you run the code, I can run the code calculating the potential at z equal to 1 with the square of size 1, and then I use 5 squares along the x direction and 5 squares along the y direction, and I'm using the midpoint rule. If I do this and using 5 points and equal to 5, I got this value here. If I use 7, I got similar values, but you see that on the third decimal digit, I see some different here. So you see that increasing the n from 5 to 7 to 10 to 15 to 20, I got different value. Increasing n, I get less and less change between one value and the other one. So this is our so-called convergent test. We increase the resolution of our problem, so we increase the number of square. We are calculating the total integral, and you see that the potential at z equal to 1 is converging to a given value. So you see that increasing the value, there are little bit of difference, right? At the beginning there is quite a lot of difference from going to 5 to 7, but then going from 14 to 19, the difference is basically on at this digit point. So what I can do, I can collect the data on my simulation. I take two auxiliary vectors. One is potential, that is collecting the potential values, calculating for different number of squares. So I have 4 by 4, 6 by 6, 9 by 9, 14 by 9, and 19. And then I also take the L square for the x-axis. I can plot the values of the pot using this function, MATLAB function called plot. On the x-axis I put h2, and on the y-axis I put the potential calculated with different number of squares, and then I put the labels on. As you can see, on this axis I have a square, and then I have 5. You see that the different values are basically around a line. So one thing we can do is actually to calculate, we can extrapolate what is the value of our integral for 0 cell size, so for h equal to 0. So what is actually the trick here? Well, the trick here is that we have our values for we got from integration, and we can approximate as different power of h. The scheme is a second order accurate. So what we can do is to make an expansion of our integral using h, and then we put h equal to 0, because that's what we want to do. We want to extrapolate the value of our integral when the cell size is equal to 0, so like in the continuous case. If we do this operation to extrapolation to 0 cell size, h equal to 0, this value here containing the power of h will go away, and we will keep this integral that is h naught. So h naught is going to be the extrapolated results, right? Is the one that does not depend, that is the value that is calculated for h equal to 0. How we do this extrapolation? Well, we can extrapolate the compute results as a polynomial fit in h square using the MATLAB command polyfit. The command is polyfit works as follows. It returns the coefficient for a polynomial px of degree n. That is the best fit in the least square sense for the data in y. So our data in y is going to be our potential that we calculate, and x is going to be our h square. Important things to remember that the results of this polyfit are the coefficients. Coefficient in p are descending powers, and length of p is n plus 1. So you will see this will be our coefficient with the highest polynomial order. So the one that we're interested in is a naught, so will be the last value from the polyfit. So let's do this exercise using MATLAB. I do polyfit, and I take this variable polyfit. I put x, our experimental value, and then I use just one polynomial, and this is the results. So our I naught is this value here. I keep increasing the polynomial order, right? And I got this I naught, it is our extrapolated value to 0 cell size. So I do this, and you see that increasing polyfit, I get better value, and this is going to be our extrapolated value to 0 cell size. So how to estimate convergence rate in practice? Well, in many real-world cases, for instance, when we have complex geometries, complex boundaries condition, presence of interface, and no exact solution, different parameters for the solution study, it's challenging to either to estimate the accuracy or estimate the errors, right? So the example we saw is quite similar to calculate the truncation error, but basically finishing a certain, but basically truncating our expansion at a certain point to say, well, this is the truncation error. In many cases, it's not really possible. So how we do in practice? Well, the strategy that we typically do is that we perform a simulation with very high resolution and take these results as the exact solution. So let's take very, very high resolution simulation, and then take the results of this high resolution as the exact solution. And then we can compare other resolution with the lower resolution to this exact solution. So for instance, we can calculate error with cases with a smaller h, and we also assume that the round error is small, so it's going to be mostly truncation error. And then we plot h square, h cube on the same plot. So just to give you an example how we can do in our practical example calculating the potential along the z direction. So we have here, we calculate as our exact solution the potential using 1,000 squares in one direction and 1,000 square in the other direction. We take this very high resolution results as our exact solution. So we take this solution. The other approximate solution will be the one that use way less number of squares in our domain. So for instance, we can use 20 by 20, 40 by 40, 60 by 60, and 80. We can calculate the error by comparing the values of our integral using a small number of grid points. So for instance, 20 by 20, with the one that we consider exact solution, that is the one with the high resolution using 1,000 grid points. And we can calculate the errors in this way, which is just going to take, for instance, the absolute values of the difference of the potential from the experiments and this exact solution that is highly resolved. Once we get this error, we can actually make a plot. And so in this case here, the blue line here is the experimental things. And then just as a reference, we can plot two more lines. One with a slope that is going down as a second order, that is the red one, and then one that is going down as the third order. So here you see the respective MATLAB code that I did it. So the question is, which order is our scheme? So this blue line is represented the error that I calculated in the previous slide. And which is the order? Well, what we can do is actually compare to the slope of these two different curves. You see that the slope is equal to this red line here, right? So it's a second order, right? So this was easy because we knew already that the scheme to calculate this integral is a second order. So we knew that was the what is expected to do. So one important point I want to make is that it's very difficult to calculate, to understand what is the order by using the linear scale. So what we do, we typically use log-log scale or semi-log scale to understand the behavior of the truncation error. One interesting part is how to calculate complexity and how to calculate the number operation. Well, there is a very empirical way to calculate the number operation, that is to look at computational time. So what we can do is to use this profiling information here. We can start our profile, so profile on and then profile off in our MATLAB code. And then we can use the profile viewer command that will tell us how much time has been spent. We can calculate we can increase the number of n in this is the number of square in x direction and in the y direction. And then what we can do, we can plot the execution time depending on the number of square. That will tell you an idea of the complexity of the problem. You see that increasing n, the execution time roughly increase linearly. So as assignment, we will ask you to estimate, what is the truncation error for a different numerical scheme that is called trapezoidal rule. Of course, it's possible to use a much more refined numerical scheme, higher order discretization scheme like the trapezoidal rule that will have a lower truncation error, but of course also will have a higher number of computation. So we provide you the code and going to ask you to perform a convergence test, increasing the number of grid points and check the error, and also to perform an extrapolation to zero cell size. So one interesting point that also the book is making is that what is the integral for z equal to 0? So the integral is singular, but the integral is still converging. So we can calculate analytically this is equal to this point here. If we apply the midpoint rules, we get results that is quite good compared to analytical results. If we apply a higher order schemes to calculate the same integral, you will see that the integral is not actually converging. So this is very interesting and tell us that lower order methods, like for instance midpoints in this case, are better in dealing with the singularity. They're more resilient because they are more noisy. They have this truncation error that is coming to help for the convergence. So this is the last slide of this lecture, but also of this module. The next module, we're going to start looking at finite difference methods and finite time domain techniques for solving the Maxwell equation. Talk to you soon.